Welcome. Today's notes worksheet is entitled Probability Day 1. What I would love for us to do is to try some warm-up probability problems just to see what our comfort level is, and then we can dive a little deeper into some of the harder problems. Probability, of course, is a way to mathematically express the likelihood of an event occurring. And so we'll go ahead and formulate some ideas as we go through this lesson and a couple other ones as well. So why don't we start it out here? I'm going to run through some quick explanations. The hope is that you're either doing this with me or that you're maybe pausing and then just seeing how you did on some of these. So let's get ready to roll. Number one, a single die is rolled. Find each probability. And so this notation right here would be the probability of rolling a single die and the number coming up prime. And so what we want to do is write this as a fraction. And so if you remember your probability, basically it's a fraction of what we would call the number of favorable outcomes on top, sometimes called the number of successful outcomes. And then the denominator here would be the number of possible outcomes. And so just real quick, obviously, rolling a single die, the outcomes 1, 2, 3, 4, 5, 6. And that would pretty much be it right there. So when we talk about this fraction, I usually do the denominator first and get the possible outcomes taken care of. So 6 outcomes, and then how many of those outcomes are prime? How many of them are favorable? And so if I look at my list here, prime would be 2 distinct factors. So 2 is prime, 3 is prime, and 5 is prime. And 1 is not prime. So just 2, 3, and 5. So that would be 3 outcomes out of the 6. And so of course, there's your probability. Now you are more than welcome to express these answers as fractions or decimals or percent, whatever suits you. It really doesn't matter to me. Okay, probability that it's a double digit. So out of 6, and then how many of those outcomes are double digits? Well, it looks like 0 of them. So in this case, the probability would be 0. All right, nice. Let's keep going here. Number 2, a single card is drawn from a deck of cards. Find each probability. And so 52 cards in a standard deck. If you're unsure about some of the composition of cards in the deck, please feel free to ask. But let's go ahead and take a look. So probability that there's a red 7. So 52 cards in the deck. Red 7, basically how many of those would be out of the 52? And we have a red diamond and we have a red heart. And so there are only 2 red 7s in the deck. 2 out of 52. And there's your 1/26. There's your probability. Okay, good. Next one that I have, let's see, we've got the probability that it's not a face card. Okay, interesting here. So probability that it's not a face card. We'll go face cards as just Jack, Queen, and King, just for future reference there. So those would be 12 face cards in the deck, 12 face cards. And so how many would not be a face card if there are 12 face cards? And so I'm getting 42 on that end. So again, we're just going to go Jack, Queen, and King for face cards. There are 12 of those, 4 for each of those. So that would mean 40 non-face cards. And again, reduce fractions if you get a chance. Again, if you don't, it's not the end of the world. I've got 10/13 on that. All right, very cool. So next one, probability that it's a diamond or a club. And again, if you can shortchange this a little bit, you're more than welcome to, of course. Again, hopefully you're in fact working faster than I'm working here. So probability that it's a diamond or a club, well, there are 4 suits in the deck. And so, one of them is diamonds, one of them is clubs out of the 4. So chances are here we're going to get a 1/2 out of this. But basically, I would say there are 13 diamonds in the deck. There are 13 clubs in the deck. And so that would give us 26 total. And again, that would be a 1/2 probability. All right, good. So again, just these are the mediums that we will see with probability problems, just trying to get comfortable with it. So number 3, coins. 2 fair coins are tossed, find each probability. And so in this case, we might want to go ahead and just outline some of the probabilities with using the outcomes here. So here's what I'm thinking. When 2 fair coins are tossed, what are the outcomes? Well, on the first coin, it can be heads, and the second coin, it can be heads. That's one way that the outcomes can occur. One way it can occur is heads on the first coin, tails on the second coin. And then another way that it can occur is tails on the first, heads on the second. And the last way that I can envision the events occurring would be tails on the first, tails on the second. And so as a result here, what I see is that there are 4 outcomes when you flip 2 coins in the air. All right, fair enough. How many of those outcomes have 2 heads? Well, as you can see, it would be 1. And so the probability is 1/4 that you would get 2 heads when tossing 2 coins. Now we can roll with letter B pretty easily here, so let's do that. I've got 4 outcomes total. How many of those outcomes have 2 tails? Well, it looks same thing. It looks like just this one right here. Okay. And then last on this one, probability that it's 1 heads, 1 tails. As you can see, we've got the 4 outcomes. And how many ways out of here are we getting 1 heads and 1 tails? It looks like 1 right here and another right here. So 2 different ways that can come out. And so this looks great. 2/4, 1/2, and end of story there. All right, so we've got a die, cards, coins, looking good. Let's keep it going. All righty, number 4. How many outcomes are there when 2 dice, should be 2 dice there, are rolled together? Use the fundamental counting principle and the following table. All right, sounds good. So I created a nice little table for you, and here's what I'm thinking with this. If you guys want to box this on up, that would be great. Something like this. And so here's die 1, which obviously has 1 through 6. Here's die 2, which obviously, again, has 1 through 6. And based on what comes up on each die, add them together and you get a sum. So for example, if a 1 came up and a 1 came up, add them together, you get a 2. For example, just looking here, if I get a 3 on the first die and 2 on the second die, obviously the sum is 5. And so you can see all the sums that emerge from rolling 2 dice. And in this case, it does say use the fundamental counting principle on the table. If you were to count up all of the outcomes here, you end up getting 36 as a matter of fact. And think about that logically, of course, where that comes from using the fundamental counting principle. How many possibilities are there on the first die? There are 6 possibilities. 1, 2, 3, 4, 5, 6. How many possibilities are there on the second die? Obviously 6. 1, 2, 3, 4, 5, and 6. The fundamental counting principle says I multiply the number of possibilities for each task. And of course, guys, 6 times 6 gives us this 36 right here. So when you roll 2 dice, it looks like there are 36 different outcomes. And those sums, as you can see, some are more common than the others. So let's do number 5. Number 5, use your answer from number 4 in the table to answer the following questions. And it does say which sum is most likely. And so take a look at those. Obviously, our sums range from a low of 2 to a high of 12. 6 and 6 give us the 12 right here. But you can see different combinations produce sums a little more frequently than others. And I'm seeing on this diagonal right here, and I'm hoping you do as well, that the 7 emerges probably most often. And so as you can see, there's 6 different ways to get a sum of 7. And so which sum is most likely? There you go, 7. Which sums are least likely? Well, it looks like the 2 only shows up once in my table, and the 12 only shows up once in my table. Nice. All right. Interesting one for part C. It says the probability of rolling a sum of 4 is the same as the probability of rolling a sum of, and I guess what would be the answer there, everyone? So if you sort of looked at the probability of rolling a 4, well, there are 3 different ways you can do that, 3 different combinations that produce a sum of 4 out of the 36. So that would be a 3 out of 36. What other sum has a probability of 3 out of 36? And I'm looking down here on this diagonal. Look at those 10s, guys. 3 different ways to get a 10, 3 different ways to get a 4 out of the 36. So I'll write it as a sum of 10. Very cool. Hey, would love for you to do number 6 if you haven't already. It just says which of the following numbers cannot be the probability of an event. And so think about the numerical calculation, number of favorable outcomes over number of possible outcomes, and think about what types of numbers those would produce. And as a result, which of these values right here, be it decimal, percent, or fraction, simply are just not adequate? Okay, well, here's the ones that I would circle. You can never have a probability above 1. So again, as a fraction, the favorable outcomes cannot be greater than the total outcomes. So this answer would be just irrelevant. Cannot have a negative probability. Again, just two positive values, one on top, one on bottom. Yes, you can have a probability of 0. We saw that. That would be the event can't occur. Yes, you can have a probability of 1. That would be that the event will occur. But you cannot have a probability above 1 or 100%, so this one would not work. So basically, when we have our probabilities here, I'm hoping everyone kind of realizes this piece, probabilities are going to be anywhere between 0 and 1 inclusive. Okay. So again, just a mathematical explanation on the likelihood of an event occurring. Closer to 0, not likely. Closer to 1, more likely. Beautiful. All right, guys, let's go ahead and get in a little deeper into some of these problems and refer to sort of the counting principle a little bit, and I will go from there. So the review at the top, it says, in counting, how do we find the union, and that's pretty much what we're going to be doing today, the union of two events occurring. And so just in terms of counting, the way we said it is the number of the union of two events occurring, so one or the other, is equal to the number in the first plus the number in the second. But we do have to be careful about counting things twice. That's what we talked about when we did the counting lesson. And so what we have to do is subtract away the redundancy. And the redundancy would be the intersection of the two events. So that's what we had when we talked about counting. Now, guys, what we're going to, of course, do is translate that into probability, and that's what it says right below here with this little asterisk. It says, in probability, the union of two events occurring is often used with the word or. And if you guys can circle that for me. And so one of the things we'll talk about when we look at probability and we see the union of two events, when we talk about or, everybody, we're going to talk about adding the probabilities together. Now, it's not quite that simple, as you can see, but it's basically going to be this piece up here. So, long story short, what we'll focus on today is this piece, the probability of one event occurring or a second event occurring. So that will be our union. And that is equal to the probability of the first plus the probability of the second. But again, we just have to be a little careful. We do not want to count things twice in our favorable outcomes. So what we want to do is subtract away the redundancy. And so highlight that if you get an opportunity. And that's what we'll pretty much talk about here today. Or means add. When in probability, or means add. We'll see a different buzzword come up on the next lesson, but for right now, or means add. Okay, well, let's go again, try it out here, and see what we're looking at. So example 1, a single card is drawn from a standard deck. What is the probability that we draw either a heart or a face card? So there obviously is our buzzword, heart or a face card. And let's give it a try. So I'm going to write out my notation here, kind of get comfortable with this piece, heart or face card. And so what that would be basically, or means add, so I add the two probabilities together. So I want the probability of selecting a heart, add the probability of selecting a face card. But here is the problem. There are certain cards in the deck that will be in both of these favorable outcomes here. And so I don't want to include the same card twice. That's the key. And so as a result, I have to subtract away the intersection, which would be the probability that it would be a heart and a face card. All right, so I hope that makes pretty good sense just in the setup there. I'm going to try to find a little room for this. Don't have a ton, but I'll see what I can do. But essentially, that's what we're going to do. So one more time, probability of it being a heart or a face card, exactly what the question asks. Probability of the first plus the probability of the second, but we do want to subtract away the probability of the intersection. Okay, well, let's keep it nice and easy here. I'm going to have to work off to the side, which is not ideal. Should have left a little more room for myself, but oh well. So how many hearts in the deck? I've got 13 out of 52, so 13 hearts in the deck. That sounds great. Probability that it's a face card. Well, guys, there are 12 face cards. I think we had alluded to this before. So 4 jacks, 4 queens, 4 kings. So 12 out of the 52. Now again, here's the slight problem. There are certain cards that I included both here and here. The ones that are both hearts and face cards. And so guys, just please don't forget, we must subtract. And so I subtract away the intersection here. How many of those cards are both? How many are both hearts and face cards? Well, I've got the Jack of Hearts, the Queen of Hearts, and the King of Hearts. And so as a result, I've got 3 cards that I accidentally counted twice, and I don't want to do that, of course. And so I've got to subtract those away. And I think long story short here, obviously just subtracting and adding fractions, keep the denominator, add those numerators, and I think we've got what we need. 22 out of 52. I ran out of room there, but how about 11 out of 26 would do? I'll try to write that in there if I get a chance. There we go. And that looks like a good one. Fantastic. All right, so I hope that makes pretty good sense. It's just a variation on probability. Union today. Okay, let's go ahead and do letter B. Letter B says, what is the probability that the card will either be an odd number or a black card? And so let's go ahead and put this in place, odd or black. And so I'll write out my notation. You want to do the same. Might not be a bad idea. There we go. So the probability that it's odd plus the probability that it's a black card. And then just be careful. We want to subtract away odd and black. Excellent. And so that's what this is going to look like. Let's play it out here. So how many odds in the deck? You know, it just depends. It's weird. Ace is one of those things that can go either way, to be honest. I know in value, ace is an odd number, either 1 or 11. But I was thinking of this problem literally as having an odd number on the card. So again, if you interpret it a little differently, no big deal whatsoever. I will account for that when I look at your work. So anyway, odds, I was thinking there are 4 3s, 4 5s, 4 7s, and 4 9s. Those are the ones that have odd numbers literally written on the cards. So 4 of each of those, 3, 5, 7, 9. So I've got 16. So 16 out of 52. And got to add how many black cards in the deck. Half and half here, guys. So 26 out of 52. And then what we're going to do is subtract away the ones that are both, of course. And so the ones that are both odd and black. So let's see, there are 2 black 3s. Try to count it out there. 2 black 3s, 2 black 5s, 2 black 7s, and 2 black 9s. And so as a result, I'm getting 8 out of 52. And this looks pretty good. I'm seeing this as, if I add these together, I get 42, subtract the 8, I'm getting 34 out of 52, it looks like. And I'll have to bring that on down here. So out of 26, I'm getting something along those lines. All right, good. Hey, let's try one more with this and then keep it moving. Some good examples. And again, maybe you can fast forward a little bit if you're getting the idea here. Just keep working ahead and then check your answers, of course. Letter C. What's the probability that we draw either an even number or a face card? So even or face card. And, you know, just one more time all the way through. Probability that it's even plus the probability that it's a face card minus the probability that it's an even and a face card. All right. And notice there's a quick secondary question on this as well. We'll go ahead and lay out momentarily. So probability that it's even, again, the way I interpret it literally is that it has an even number written on the card. So that would be 2, 4, 6, and 8. and 10. So 2, 4, 6, 8, and 10. And so I'm seeing that as 20 out of 52. We already said there are 12 face cards, so 12 out of 52. And then here's the key. What do you notice about the intersection here? How many cards both have an even number and have a face on it? None. None. And so anyway, we just kind of subtract 0 here. You could go ahead and write minus 0 out of 52 if you want. But basically, what we have here is that we're just adding the two probabilities together. And sorry, I'm going to have to kind of move this in. I'm going to have to go right over here. I think we get 32 out of 52. And I'm getting 8/13 on that when all said and done. So it just says, what do you notice about the intersection of these two events? I don't know. What do you want to write off to the side here? Maybe something like this. Intersection happens to be 0. So there is no overlap in this case. And when this occurs, these events actually happen to have a particular name. I won't call you on it, but you should be familiar with the idea. These are what are called mutually exclusive events. If you can jot that down, that would be great. And again, that occurs, of course, when the intersection is 0. So that's why you can really see or means add in probability. Obviously, we do have to be just a touch careful. Very cool. Let's keep it rolling. Example 2 and example 3, we'll do the coins and the dice again. So let's see, 4 coins are flipped. What's the probability that at least 3 heads will appear? All right, I kind of like this one. Let's underline that piece. At least 3 heads. I think maybe what we want to do is reinterpret that just ever so slightly here. 4 coins being flipped, we want at least 3 heads. So what that means to me is that we can either get 3 heads or 4 heads. Hopefully everyone's okay with that piece. So that's what at least 3 means to me. And again, or means add. So what we're going to do here is the probability that we get 3 heads plus the probability that we get 4 heads. Now everyone, here's of course what I would ask you. Is it possible when 4 coins go up in the air, is it possible for those coins to land and have it simultaneously be 3 heads and 4 heads? No, I mean that's actually nonsensical. That's just not going to happen. So in this case, they're mutually exclusive. So as a result, all we're going to do is add those two probabilities together. There is no intersection. All right, well let's play it out. Again, I'll have to come over here. Sorry about that. So when 4 coins go up in the air, if we want to kind of talk about the outcomes that occur, I'm going to use a little counting principle here to get this going. Trying to find a spot for me to sort of think about this. Think about when 4 coins go up in the air. How many possibilities are there for the first coin? 2. How many possibilities are there for the second coin? 2. How many possibilities for the third coin? And how many possibilities for the fourth? So I am hoping you would agree with me that when 4 coins go up in the air, there are really 2 times 2 times 2 times 2 possibilities. And so your total outcomes here, the possible outcomes, would be 16. All right, so 4 coins go up, and I know that the denominator is going to be 16. So let's get that in place. Now, I do believe we've seen this a little bit before, actually, when we talked about combinations. Kind of made you look at this. So the question at the top would be, how many ways can we get 3 heads from those 4 coins? And what we decided, not sure if you remember this from a few days ago, but what we basically decided is that this is a combination. So we have 4 coins, and there are different ways to group 3 of them. And so as a result, it should be 4C3. And how many ways can we get 4 heads from the 4 coins? What we found, everybody, again, we kind of did the work behind this, that what we found is that it's 4C4. And as a matter of fact, 4C4 happens to be 1. There's only one way you can get 4 heads and 4 coins. So this is going to be a 1 over 16. How many ways can we get 3 heads on 4 coins? Well, as a matter of fact, 4C3 is 4. And if you were to list all the outcomes there and count how many of them had 3 heads, there are 4 ways you can do that. So anyway, that's how this problem plays out. And we get just a 4 out of 16 plus a 1 out of 16, and there's your 5/16. Cool. All right, next one. Letter B. What's the probability that at most 1 heads will appear? Interpret, everybody. At most 1, well, that would be 0 heads or 1 head. And so what we would do is just take the probability of getting no heads plus the probability of getting 1, and you'll see it plays out the exact same. So 4 coins here. No big deal, guys. Everyone give me a 16 on the bottom for each. 16 possible ways it can come out. How many of those ways have no heads? Well, it would be 4C0, which as a matter of fact is 1. How many ways have exactly 1 head? 4C1. And again, you're more than welcome to investigate this further and inquire kind of why combinations works. Be happy to show that to you, of course. But you get the same deal. 4/16, 1/16, 5/16. Cool. Letter C. Let's keep it rolling. Odd number. Again, interpret. What does that mean to you? An odd number of heads when 4 coins are flipped. So what that means is either 1 head or 3. And so we would take, again, or means add. Sorry for being redundant, but it does help. Plus the probability of 3 heads. All righty, let's let it go. 2 fractions. 16 as the denominator in both. 4C1, 4C3. 4 coins, 1 heads. 4 coins, 3 heads. And by the way, when you do this, you get 4 out of 16. When you do this, you get 4 out of 16. And so you can see, guys, 8 out of 16 should be a 1/2 probability. Cool. All right. Let's do example 3, and then we've got one more pretty interesting problem to take a look at after that. But let's move into the next medium. 2 dice are rolled. What is the probability that the sum will be prime? All right, interesting. So you might see me kind of go back a little bit. And you're welcome, by the way, for giving you this table right here. So these are all the ways this can occur. So 36 possibilities. Keep those in mind. I'll be going back to it. So just what is the probability that the sum will be prime? All right, guys, give me a 36 on the bottom, and let's keep this moving. So how many of those outcomes out of the 36 would produce a prime sum? Let's count them up here, everyone. You ready for this? Primes, guys. 1, 2, 3, 4, 5, 6, 7. So different ways to get these prime sums. I'll go one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's find some more primes. 8's not prime, 9's not prime, 10's not prime. 14, 15. I'm getting 15. Okay, again, I don't want to highlight too many of these, but let's see. All of these, I guess I'll do it. All of these are prime sums. Here we go, just in case you didn't catch that. Those are all the prime sums right there. Different ways to get them. And so out of the 36 different possibilities, there are 15 ways to get a prime sum. All right, so everyone, if you would, letter A, 15 out of 36. Beautiful. Letter B, what is the probability that the sum will be double digits? All right, so 36 possibilities. Let's go back to that beautiful table. And again, you're welcome for putting that in. Here we go. How many of those sums are double digits? Let's see, right here, 1, 2, 3, 4, 5, and 6. Everyone okay with that? These are the sums that are double digits. 6 different ways that I can produce them. All righty, good, good, good. So we've got that 6 out of 36 right there. Now it's time to make it happen with letter C. Here's the key. What is the probability that the sum will be prime or double digits? Now let's see if we can put it all together, everyone. Or means add. So I take the probability that it'll be prime, 15 out of 36, plus the probability that it will be a double digit, 6 out of 36. Everyone, am I done? No, because a couple of those I counted twice. I don't want to count things more than once. That obviously skews the calculation. And you go back here, and what I would do is find the probability that they are both prime and double digits. And if you kind of take a look, I'll go ahead and circle this one and this one. Do you see we counted those two 11s? We counted them twice, and we can't do that. So as a result, we subtract away the intersection. The intersection would be the probability that they are prime and double digits. So please just be careful on that. There is the overlap, and so we do have to account for it. Let's see, what do we get there? 19 out of 36. And there you have it. Cool. So again, or means add, but just be careful about the overlap. Subtract away that redundancy. Okay, let's go into one more. This is not an or problem. It's not a union problem. It's just a very interesting probability problem. So let's try it out here, see what you think, and we'll wrap it up on this one. So example 4 is the birthday problem. And it says, what is the probability that in a group of 10 people, so picture you and 9 other people, out of those 10 people, at least 2 people have the same birthday. And we'll skip the idea of leap day, so 365 days in the year. All right, well, let's see if I can break this down for you as best as possible. And then if you have questions on it, just please let me know. So let's check this out. It's kind of interesting. Letter A, how many possibilities are there for each person? All right, well, fair enough. Are you okay for you and for each of the 10 people in the group? There are 365 possibilities. You can be born on any one of those 365 days. So how many possibilities are there for each person? Obviously 365. Now here's a great one. Letter B, let's extrapolate a little bit now. How many possibilities are there for all 10 people? Now let's put it all together. So I said for each person it's 365. So for the first person, 365 possibilities. For the second person, 365 possibilities. For the next person, 365 possibilities, right? Dot, dot, dot. Everyone cool with that piece? So in this case, how many possibilities are there total? This, by the way, will be our denominator when all is said and done. We look at 365 raised to the 10th, right? Each person has 365 possibilities. Okay, it's going to be a large number. Now here's the thing with this one, and it's sort of this piece right here. We're going to kind of take a look at it from a different perspective. So letter C, it says, rather than trying to count the number of ways that at least 2 people have the same birthday, let's count the number of ways of its, what's called its complement. Now the complement is basically the opposite of that event occurring. So in this case, and we saw this before, I think, when we worked with Venn diagrams. So what would be the complement of at least 2 people having the same birthday? Well, again, we're looking for the opposite. So if the event we're looking at is at least 2 people have the same birthday, then the complement of that, the exact opposite of what we want, would be, in this case, the number of ways that no 2 people have the same birthday. So write that in there for me, and that's how we're going to take a look at this. So no 2 people have the same birthday. That would be the complement of at least 2 people having the same birthday. fine. Now, I hope that makes sense, because now we're going to focus on this particular piece and then do our mathematical calculation at the end. So it says, to do this, let's focus on one person at a time. So again, now what we want is nobody having the same birthday. So how many favorable outcomes are there for person number 1? So there you are person number 1. Nobody's recorded in terms of their birthdays just yet. How many favorable outcomes are there for you? Well, I would argue that you could have any one of the 365 days as your birthday, and you're fine. You haven't negated this just yet. But person number 2 has a little bit of a condition. Would you agree with me that person number 2 can't have your birthday? Otherwise, that negates this right here. So if we want no 2 people having the same birthday, then person number 2 only has 364 possibilities. Can't have your birthday. Now person 3, is everyone cool with this? Person 3, if we don't want anyone to have the same birthday, person number 3 can't have this birthday or this birthday. Can't have the birthday of person 2 or person 1. And so would have only 363 possibilities. And do you see what would happen then for person 4, for person 5, for person 6, etc., all the way to person 10? So I guess the way I would say this is, this would be the probability of no 2 people having the same birthday. Excuse my shorthand on it, but I want to get this moving along. So is everyone okay with me saying something like this? The bottom would be 365, 365, 365, all the way through. And let's go ahead and do it as 365 to the 10th. Now the top, I'm curious if it looks familiar to you. The top, again, what we already decided is the first person doesn't matter. But the second person can't have that birthday. Second person, or the third person can't have either one of those birthdays, etc., all the way down to the 10th person, which would only have 356 possibilities. Okay, which actually, again, wow, this is just great mathematics coming through here. The bottom, there's your total. That's how many possibilities, how many birthdays are possible for 10 people. For no 2 people to have the same birthday, we already decided that it would be 365. Oops, sorry, wrong one on my part. Let's get rid of that. It's a permutations. And again, if you did this calculation right here, that should look familiar. We've done that before. 10 people from a group of 365 birthdays, and we arrange them. Cool. Now guys, this would be the probability that no 2 people have the same birthday. Let's get that. I'm going to bring my calculator up, and again, we'll wrap this up momentarily. Stay with. I think it's a good little problem. So 365, I go under math. So 365 P10. Oops, and I accidentally hit 11, so let's do that again. 365 P10. There we go. And I've got that piece right there. I'm going to now divide that by 365 raised to the 10th. And so what we have going here is that the probability that no 2 people have the same birthday is about 88.3%. All right, so I'm going to write that right here. 88.3. That would be the probability that no 2 people have the same birthday from a group of 10. So, last but not least, so it says, oh, we have that right here. Never mind. So 883, put that in. We already did that. Now, guys, letter E. Now determine the probability that at least 2 people have the same birthday. Again, it's the complement of that. So we know it's going to either be nobody has the same birthday or at least 2 people have the same birthday. And their probabilities have to add up to 1. So if we do 1 minus this, there you go. There is an 11.7% chance that at least 2 people would have the same birthday from a group of 10. Kind of cool. What happens, what's kind of fascinating about this, and then again, I promise I'll wrap this up here. When you get to about 23 people, it's just about 50%. So if you have 23 people and you ask for all the birthdays there, the probability that at least 2 people have the same birthday is about 50-50. And then what's kind of crazy is when you get a group, it just starts escalating dramatically. When you get about 60 people, and again, it doesn't seem dramatically large, but when you get about 60 people, the probability that at least 2 people will have the same birthday is over 99%. Kind of cool. Interesting problem. Again, just very complicated, but I think pretty relevant and pretty interesting. All right, guys, I'll wrap it up right there. Thanks for listening, of course, and please ask questions, especially on that last one.